Namaste, welcome to Pythagoras Academy. In today's video, we'll try to understand Newton's first law and second law. Students are pretty much familiar with these laws from 8th standard and 9th standard of their schooling. But the problem with Newton's laws is Sir Isaac Newton has given his laws in the language Latin. Those laws have been translated into English, and again they have been simplified into your textbooks. In this entire process, the whole essence of Newton's laws is lost somewhere. So that is the reason many students will have misconceptions about Newton's first law and second law, and they fail to apply these laws properly. But the entire classical mechanics is dependent on Newton's three laws of motion. Without clarity of this in this Newton's first law and second law, a student cannot solve a problem of mechanics. So this video is going to clear every misconception that you have about Newton's first law and second law. So coming to the first law, which is also called as law of inertia, it states that every body continues to be at rest or uniform motion until and unless compelled by a net external force. This statement you have been studying since your schooling. So let me try to explain it much better. Somehow, to me, this statement gives an impression that net external force causes motion, because it says that every body continues to be at rest or uniform motion. Of course, uniform motion is mentioned, but when students read this statement, it somehow gives an impression that net external force causes motion, but it is not so. The whole intention of Newton's first law is to say that net external force causes acceleration. So that would be the right way to understand Newton's first law of motion. If you ask me to rephrase Newton's first law, I would say it is net external force that causes acceleration to a system. Suppose if there is a body which is at rest. Let us go to the next slide. Suppose there is a body which is placed on ground and it is at rest. There is no motion. It doesn't mean that there are no forces acting on it. Still there are two forces acting on it. One is its own weight mg acting downwards, and the other one is the normal force exerted by the surface on the body. There are two forces acting on the system, but the net force is zero, so the body is at rest. So that is the reason we have to be very, very specific with the word net external force. It is not a single external force, it is the net external force, which is the vector sum of all the forces acting on the system. So when there is a net external force, it causes acceleration. In this particular case, net external force is zero, it is at rest. Suppose if there is a body which is on the ground and you give a push to it, then it starts moving in the rightward direction, and it comes to stop by itself because of the friction acting on it. So it is friction which is acting opposite to its motion. So this friction is the net external force acting on the system now, and this is causing acceleration. So now acceleration is opposite to the velocity of the body. So the velocity certainly decreases and it comes to stop. So this is the reason I said that net external force causes acceleration. It is not that net external force causes motion, because in this example you can clearly see that net external force is seizing the motion. It is also stopping the body. So net external force can cause motion, and if there is already motion, net external force can bring it to stop. So precisely net external force causes acceleration. Suppose there is a body on the ground, there is a string attached to it, and you started pulling it. Say the surface is rough, the surface is smooth, so there is no friction. So when you apply this force F towards right, net external force acting on the system is towards right, so there is acceleration in the rightward direction. So the body would accelerate and move by gaining velocity from rest in the rightward direction. So let me write down here that Newton's first law is net external force causes acceleration. Or to be more precise, I would say net external force acting on the system by implies net external force is equal to 0 by implies acceleration is 0, which says that if net external force acting on the system is 0, then its acceleration is 0, or if acceleration of the system is 0, then we can conclude that net external force is 0. Both ways, net external force acting on the system is 0 by implies acceleration of the system is 0. So this is like the mathematical form of the statement net external force causes acceleration. And Newton's first law is only talking about one case out of infinite possible cases. That what if net external force is 0? If it is 0, then acceleration is 0. If net external force is not 0, then acceleration is also not 0. And Newton's second law will address all those infinite possibilities. What if net external force is not 0, non-zero? If net external force is 10 newtons, what is the acceleration? If net external force is 20 newtons, what is the acceleration? So that is addressed by Newton's second law. Net external force acting on a system is equal to the rate of change of its linear momentum with respect to time. So most of the students will conclude or will come into a conclusion that Newton's second law is F is equal to ma, but it is not that. Newton's second law is net external force is rate of change of its linear momentum with respect to time. From this, we can derive that F net is equal to d into momentum is the product of mass and velocity with respect to time, and this is m into dv bar by dt. So momentum is product of mass and velocity. Out of this differential operator, I am bringing m out. I can do this only if mass of the system remains constant. There can be variable mass systems, for example, a rocket which is propelling. So in the rocket propulsion, the mass of the rocket is continuously varying. The rocket is losing its mass, shedding away its mass. So it comes under the variable mass system. So if it is a variable mass system, you cannot bring this m out of this differential operator. You have to apply UV rule here. For a constant mass system, it is m into dv by dt, of course dv bar by dt, which is a bar, rate of change of velocity, which is acceleration. So from this we can deduce that net external force is equal to mass into acceleration divided by mass, provided it is a constant mass system. If it is a variable mass system, then it's a different analysis altogether that I will try to discuss in another video some other time. So this is all about Newton's first law and second law with clarity. And there is another important thing about Newton's first law and second law. So now that you have understood Newton's first law and second law, if I give you a situation like this, that there is a tree and there is a car which is moving with some acceleration. The tree is fixed to the ground, obviously. So acceleration of the tree is 0. Acceleration of the car is ai cap. It is a units along positive x-axis. Now, if there is a person A who is standing on the ground and trying to apply Newton's first law or second law on the tree, there are two forces acting on it. One is the own weight of the tree, the other one is the normal reaction. And so in the vertical direction, net force is 0, acceleration is 0, it's perfect. In the horizontal direction, it is at rest. So the body is at rest, it means that acceleration is 0. And from Newton's first law and second law, if acceleration is 0, net force is 0, and there is no net force to be observed here, and Newton's first law and second law are working just perfect. But if there is a person B inside the car and he is trying to apply Newton's first law or second law on the tree, then with respect to person B, acceleration of the tree with respect to B is equal to acceleration of the tree minus acceleration of the person B. Acceleration of the tree is 0. Acceleration of the person B is nothing but acceleration of the car, which is ai cap. So acceleration of the tree with respect to the person is minus ai cap. It means that B observes that tree is accelerating towards left with an acceleration a. And with respect to B, the forces acting on the tree are mg downwards, normal force upwards, vertical direction, there is no motion, there is no acceleration, net force is 0, it's perfect. But when it comes to the horizontal direction, there is acceleration, but B do not observe any force which is producing this acceleration, which violates Newton's first law and second law. Because it is very clear that there is acceleration, and according to first law or second law, if there is acceleration, there must be some net external force which produces this acceleration. But according to B, there is no force acting on the tree in the horizontal direction. So Newton's first law and second law will fail in this particular scenario. The reason being, the car is accelerating. So Newton's first law and second law have a limitation. They cannot be applied from any frame of reference. So just think of it, why Newton's laws are failing in this particular scenario. I'll try to cover this concept in the next video. Thank you.